This is Lesson 9, Unit 11, Titrating a Weak Acid with a Strong Base. So here we have an image of titrating a weak acid with a strong base. So what we have is 26.5 mLs of a weak acid, which we'll call HA, is titrated with 0.076 molar KOH. So I've labeled it on the burette here, and then what we have in the flask. For now, I don't want you to worry about this. We're going to come back to it later. I just want to talk about what is going on in this curve here. So initially, we look at our pH, and it is about 3. This is a 0.1 molar solution, as we're going to figure out later, yet the pH is only 3. This is because this is a weak acid, so it does not dissociate completely when we have it in water. The initial pH is going to increase very rapidly, and this is characteristic of a weak base. So we see an initial sharp pH increase. Once we get past the sharp point, we have a relatively level area here where the pH increases rather slowly, and this region in here is going to be called the buffer region for reasons that you'll see as we start into the calculations. So right in here is called our buffer region. So we get a buffer region. If we look here at 35 mLs, we have our equivalence point. Notice that the pH here is greater than 7. This is characteristic of weak acids, and we'll go through the calculation on why the pH is always going to be greater than 7 for weak acids. So this is one way you can pick out a weak acid titration curve, is the pH is going to be greater than 7. This happens to be 35 mLs. So at 35 mLs, we can use that MAVA is equal to MBVB, and we will use that at the bottom of this page. If we divide 35.5 by 2, we end up at this point right here, which is 17.5. And this is a very interesting point. This is the particular area where our concentration of HA is going to be equal to our concentration of A minus. Notice this means that we have made a buffer right at this point right here. So this is why we call this the buffer region. Right in the center we have a perfect buffer with equal capacity for base and for added acid. But in this region here we also have buffer combinations. Once we get beyond the equivalence point here, where we can calculate the concentration of our acid, we begin to have an excess of the base, and eventually we see the titration curve level off. Okay, so let's take a look at the reactions that were taking place here. As the titration proceeds, we have the weak acid reacting with KOH, and this reaction goes forward 100%. The net ionic equation is HA plus OH minus. We have to keep this as HA because it is a weak acid, and we can see that we are making a conjugate acid-base pair. So let's look at some of the features which I've already done for you up in the picture. The initial pH is going to be lower than 7. The initial hydrogen ion concentration is lower than the initial concentration of HA because only a fraction of the HA ionizes. So if we have our initial concentration, we've got an equilibrium going on, H plus plus A minus. Whereas if we had a strong acid, it went 100%. The pH increases rapidly for the first 5% of the titration towards the equivalence point. Then it's going to increase slowly in the buffer region because we're going to have substantial amounts of both A minus and HA present. At the half equivalence point, and this was 17.5 mLs for this titration, pH equals pKa. This is incredibly important. We're going to be using this later. And then the equivalence point at pH is greater than 7. Here's why. When we reach the equivalence point, we have equal moles of each of these. So we have 1 to 1. That's why we call it an equivalence point. We've matched the moles with the moles. At this point, we have converted everything to A minus. So only A minus remains, only the conjugate salt. This then sets up in an equilibrium with water, where we are going to be making the weak acid and some hydroxide solution. This is going to make the solution basic. So it's going to make the solution basic, which means your pH is going to be greater than 7. We can use the mLs at the equivalence point to solve for the unknown acid concentration. And then after the equivalence point, we're going to have the pH climb rapidly as hydroxide becomes the excess agent. So let's solve the concentration problem. We had MaVa equals MbVb. And you're going to have to trust me on this. The molarity of our base was 0.076. That was in the page above. The volume of the acid was 26.5. The volume of the base that comes from the equivalence point was 35 mLs, which leaves us only having to solve for Ma. And when we do that, we determine that Ma equals 0.10 molar.